friends, welcome back. This is Sakshi Kakde, and in today's session we are going to see what are trees in data structure. So let's move ahead. So whenever we listen to the word trees, we imagine something like this, isn't it? That is a tree having roots at the bottom whereas leaves at the top. So it is exactly the similar in data structure but is in inverted manner. That is, the leaves are at the bottom whereas the root is at the top. So let us see the definition of tree, what exactly it is. So tree is a finite set of one or more nodes such that there is a specially designated node called the root. So guys, remember one point, that in each and every tree in data structure, it is having only and only one root node. Again, the remaining nodes are partitioned into n greater than equals to 0 disjoint sets from T1 up to Tn, where each of these sets is a tree. And we call this T1 up to Tn the subtrees of the roots. So again, let us move forward to the next point, that is the level and depth, and we will see all the points which are related to a tree. So let us consider that this is my tree which is having all these nodes present in it. And it is consisting of a root node. In this case, the root node for the tree is A. So the first point is node. So the each and every element into the tree is called as a node. So A is a node, B is a node, C is a node. Again, all these nodes are present in a tree. So in this tree, there are total 13 nodes present. Again, the next point is the degree of a node. So basically, when a node is connected to its children, then the number of children is called as the degree of node. If we consider the example for A, B and C and D, then A is the parent of B, C and D. That is, B, C and D are the children of A. Hence, the degree of the node is 3. Again, if we consider the case for B, so it is having two children, that is E and F. And hence, degree of B will be 2. Again, if we consider the case for M, so it is having no children and hence the degree for M will be 0. So the next point is leaf or terminal. So if a node is having its degree of node as 0, then we can call that node as a leaf or terminal node. So in this case, the K, L and M are the leaf or terminal nodes. Again, the next point is non-terminal nodes. So all the nodes except the leaf nodes in a tree are called as non-terminal nodes. So in this example, all the nodes except K, L and M are the non-terminal nodes. Again, the next one is parent. So basically, a parent is children's parent in a tree. So in this case, A is the parent of B, C and D. Again, if we consider the example for B, E and F, then B is the parent of E and F. Again, if we consider the example for C and G, so C is the parent of G. Again, the next point is children. So basically, the children of parent are called as children in a tree. So if we consider the case for A, B, C and D, so B, C and D are the children of A. Again, E and F are the children of B. Again, M is the children of H. So the next point is sibling. The nodes which belong to the same node, or we can say that the node which belongs to the same parent are called as siblings. So in this case, if we consider A, B, C and D, so B belongs to the parent A. Again, C belongs to the parent A and D also belongs to the parent A. So B, C and D are the siblings. Again, E and F both belong to the same parent, that is B, and hence E and F are also siblings in this case. Again, the next point is the degree of tree. So basically, in a tree, the degree of a node which is maximum in the whole tree is called as the degree of a tree. So in this case, the maximum degree of a node is 3 and hence the degree of the tree is also 3. Again, the next point is ancestor. In simple words, we can say that child's parent's parent is the ancestor of that child. So if we consider the example for G, so G's parent is C and again C's parent is A and hence A is the ancestor of G. Again, the next point is the level of node. So this is basically how we can represent the levels of node. That is, the root node is at the first level. Again, the remaining nodes are second, third and fourth levels. Again, the next point is the height of a tree. So, the maximum level of node in a tree is called as the height of tree. So, in this case, the maximum level of a node is 4 and hence the height of this tree is 4. So, these are all the points which are related to a tree in data structure. So, we will see this all points with the definitions. So, the degree of a node is the number of subtrees of the node. Again, the node with degree 0 is a leaf or terminal node. A node that has subtrees is the parent of the roots of the subtrees. The roots of these subtrees are the children of the node. Children of the same parents are siblings. And the ancestor of a node are all the nodes along the path from the root to the node. So let's move forward towards the next point, that is the representation of trees. How we can represent a tree through a list representation. So this is how we can represent a tree through a list representation. So in this case, the first node is A, or we can say that the A is the root node in this case. So A is having the children as B and E. Again, B is having the children E, and again E is having the children as K and L. So the root comes first, followed by a list of subtrees. So this is how we can represent a tree through a list representation. So let's move forward towards the next point, that is the left child and right sibling. So basically each and every node in a tree is having the three parts. The first one is data, second one is the left child and the third one is right child. Maybe the left child or right child can be absent. So let us consider that this is my tree in which A is the root node. So we can say B as the child as it is at left position and C as the sibling as it is at right position. So this follows the rule of left child, right sibling. That is, A's children are B, C and D. And hence B, C and D are siblings. So the left one is called as the child, whereas the right one is called as the sibling. So let's see the next point, which is of binary trees. So what are binary trees? So basically a binary tree is a finite set of nodes that is either empty or consists of a root and two disjoint binary trees called the left subtree and the right subtree. And tree can be transformed into binary tree by left child and right sibling representation, which we have seen in the earlier slide. The left subtrees and the right subtrees are distinguished. So let's move forward and see what is a full binary tree. So a binary tree is a full binary tree if every node has 0 or 2 children. The following are the example of a full binary tree. We can also say a full binary tree is a binary tree in which all the nodes except leaf nodes have 2 children. Or in simple ways, we can say that if a tree is having its degree of node as either 0 or 2, then it is called a full binary tree. Let us consider the case of this tree. In this case, A is the root node. If we take the degree of node 1, then its degree is 2 as it is having two children 2 and 3. Again, if we consider the case for 2, so it is having no children and hence the degree of 2 is 0. Again for 3, it is having two children as 6 and 4 and hence its degree is 2. And similarly for 6, it is 0 and 4, it is 0. So guys, you can see in this diagram that each and every node is having the degree of its node as either 2 or 0. And hence this binary tree is called as a full binary tree. Let us see the next point, which is of a complete binary tree. So basically a binary tree is a complete binary tree if all the levels are completely filled except possibly the last level, and the last level has all keys as left as possible. So in simple ways, we can say that if a binary tree is having the degree of all nodes either 0 or 1 or 2, then we can say that binary tree as a complete binary tree. So again, we will consider this example. So in this case, the degree for 7 is 2, as it is having the two children as 5 and 9. Again, if we consider the case for 5, it is having one children as 2 and hence its degree is 1. Similarly, for 9, it is 0 and 2, it is 0. So we can see in this diagram that each and every node is having the degree as either 0, 1 or 2, and hence we can call this binary tree as a complete binary tree. So let's move forward towards the next point, which is the binary tree representation. So if a complete binary tree with n nodes, that is depth equals to log n plus 1, is represented sequentially, then for any node with index I, 1 less than equals to I less than equals to n, we have parent I is at I by 2th position if I not equals to 1. Again, the left child is at 2ith position and the right child is at 2i plus 1th position. So let's move forward to the next point, that is link representation. So as we know that each node is having three parts. The first one is data, the second one is the address of the left child, and the third one is the address of right child. So this is how we can write the structure of a node in a tree. So basically it is having the 3 points, that is the integer data, then 3 pointer left child and right child. This 3 part, it consists of 3 parts. Again, let's move forward towards the point, that is traversal or recursive version. So unlike linear data structures, that is array, linked list, queues, stacks, etc., which have only one logic way to traverse them, trees can be traversed in different ways. So following are generally used ways for traversing trees. So these are in order, pre-order and post-order. So we will see all these traversals one by one. So the first one is in order traversal. So let us consider the case of this small tree which is having the root node as A, left child as B and right child as C. So we can write the structure for in order traversal as shown below. So in order traversal, the data part is in middle followed by the right child. That is, first left child comes, then root and then right child. So in this tree, the left child is B, the root is A and the right child is C. So we can write its in order traversal as B, A and C. Again, the second point is of pre-order traversal. So again we are considering the same example of this tree and we can write the structure of pre-order traversal as given below. That is, first data part comes which is followed by the left child and right child. That is, first root comes, then left child and then right child. So in this case the root is A, left child is B and right child is C. So the pre-order traversal for this case will be A, B and C. So the third traversal is basically the post-order traversal. Again we are considering the same example and the structure for post-order traversal can be written like this. That is, in this case the data part is written at the last. That is, it is following the sequence of first left child, then right child and then the root. So in this case the left child is B, the right child is C and the root is A. And hence the post-order traversal will be B, C and A. So let's move forward towards the next point, that is threaded binary trees. So too many null pointers in current representation of binary trees. We can see that in the last trees, the last nodes are null pointers, or we can say that they are not having any of the children. So n is the number of nodes and the number of non-null links are n minus 1. Again, the total links are 2n and the null links are n plus 1. Replace these null pointers with some useful threads. If pointer of left child is null, then we have to replace it with a pointer to the node that would be visited before pointer in an in-order traversal. Again, if pointer's right child is null, then we have to replace it with a pointer to the node that would be visited after pointer in an in-order traversal. So we will see this with an example. So let us suppose that this is my tree, which is having a root node as A, and we have to consider the in-order traversal for it. That is, it is following the sequence of left child, root, and then right child. So according to that case, the in-order traversal will be this one. So we can see the case for H. It is having no childrens, and if we see in the in-order traversal, it is having no left part. So we have to make the left part or left child of H as null pointer, and we have to give the right part to the D. So it will become something like this. Again, if we consider for I, then its left part is D and right part is B. So we have to make something like this. Again for E, it will be like this. For F, like this. And again in the case of G, it is not having the right part in the in-order traversal, and hence we have to make it as a dangling pointer. So this is basically what is threaded binary tree is all about. So let's move forward towards the next point, that is of heap. So basically a max tree is a tree in which the key values in each node is no smaller than the key values in its children. A max tree is a complete binary tree that is also a max tree. Again, a minimum tree is a tree in which the key value in each node is no longer than the key values in its children. A mean heap is a complete binary tree that is also a mean tree. So let's see the example of max heap, and the property here is if the root of max heap contains the root of max heap contains the largest value, whereas the root of mean heap contains the smallest value. So if we consider this as a tree, so in this case 20 is my root value, and we can see that in this case the value of the root is maximum, whereas the all other values than the root are smaller than the root value. So this is what max heap is. Again, the next one is the mean heaps. So if we again consider this as a tree which is having the root node as 2, so in this case the value of the root node is minimum. We can compare this with the remaining nodes. In this case, the 2 value is the minimum in all the nodes, whereas all other nodes are greater than the root node. So this is what mean heaps are. So let us move forward and see the examples of insertion to a max heap. So in this case, the initial location of new node is shown by this light green color. So we have to insert an element over here. So how we can do that in max heap? So if we want to insert 5 into heap, then it will go at this position and 2 will come down, as you can see in this diagram. Again, we can insert too many elements into it. If we want to insert 21 into heap, then the 21 will become my max element, and hence it will become my root in this max heap. We all know that in the upper side or the root is always maximum in a max heap, and hence as 21 is the largest number, so it will become the root in this case. So the next is the examples of deletion from max heap. So how we can delete elements or nodes from a max heap? So if I want to delete this 10 element, or then first I need to remove the node or root node from my heap, or we can say that from my tree. So it will something become like this, that the 10 will become at the root position. And again we can rearrange that by using the property of max heaps. So this is what deletion of root node in a max heap. So again the next is binary search tree. So every element has a unique key in binary search tree, or we can say that it is a BST. Again, the keys is in a non-empty left subtrees are smaller than the key in the root of subtrees. Again, the left and right subtrees are also binary search trees. So let us see some of the example of BST. So if we consider this as a tree, so in this case 20 is the root node, and you can see guys that in the left subtree is having all the elements which are smaller than the root node. Again, the left subtree is also a BST, as we can say that 15 is the root node, and in its left part it is consisting of all the elements which are smaller than the root, and right part is consisting of all the elements which are greater than root. So in this case, as 14 is smaller than 15, so it is placed in the left part of 15, whereas as 18 is greater than 15, so it is placed in the right part of 15. So the left subtree is also a binary search tree. Again, the right subtree is also a BST, as it is consisting of, if we consider that 30 as root node in that, so as 25 is smaller than 30, so we have placed it in left position. So this is following the condition of BST, that is, in the left subtree of the root node, all the elements which are smaller than the root node are present, whereas in the right subtree, all the nodes which are greater than the root are placed. So this is what BST. Again, this is the example of BST. If we consider the root node 30, then 5 is smaller than 30 and hence it is placed in the left part. Again, 2 is smaller than 5, so it is again placed in the left part of 5. Again, this is one more example of BST. In this case, all the elements 70, 65 and 80 are greater than the root node, that is 60, and hence they are put on the right side of the tree. So these are all the examples of BST. So how we can insert a node in BST? So if we consider this as my tree, which is having a root node 30, so if we want to insert an element 80 in this, so what will happen? First, we need to compare this value 80 with the root node, that is 30 in this case. As the value 80 is greater than 30, then we have to go in the right subtree of this tree. So again, we need to compare this 80 value with the node 40. In this case, again 80 is greater than 40, and hence we need to keep this value 80, or we need to insert this node 80 in the right part of the 40, or we can say that in the right subtree of 40. So the 80 will basically come over here, and this is how we can insert nodes in BST. Again, if we want to insert a element or a node 35, so first remember this point. Whenever we want to insert a node, then first we have to compare with the root node. So first I will compare that with 30. So as it is greater than 30, then I will go to the right subtree. Again here I will compare that node with 35. As in this case 35 is less than 40, so it will go to the left part of 40. So this is how we can insert nodes in BST. Again, deletion for BST. So if we consider this as my tree, and if I want to delete a node, that is 60 in this case, so how it will work? So after deleting the element 60 or the node 60 from my tree, so it will look something like this. That is, 40 will remain as it is, that is the root node, while deletion remain as it is in the tree. The 55 will come in the upper position and the remaining elements will be arranged like this. So this is how we can delete a node in a BST. So this was all about today's session of trees. I hope that you guys are now clear with the concept of trees. So thank you for listening to the session. Thank you.